Nobody has been inside the tokamak for quite a while. We've run the tokamak really quite ferociously up to the end of its life, trying to break lots of records, which we've done. This all has an effect on materials. So sample retrieval means we get into the tokamak early, we take out some of our most interesting and complex materials, and we do all of our experiments, our analysis on these materials so that we know what the rest of the tokamak system will look like. Gives us a really good early opportunity to benchmark all of our predictive models and our studies to date and see how far off we are, if we are at all. And then we can subsequently plan for how we manage those materials through a process. Characterization is simply finding out material properties or properties of things that we have in our tokamak. They might be the physical properties, the chemical properties, or the radiological properties. The tokamak is an incredibly hostile environment at times. It's really high temperatures, 100, 150 million degrees. There's a lot of fusion fuel flying around. There's a lot of fusion neutrons produced. These all impact our materials inside a tokamak. So it's really important that we find out how our materials are affected and how we can then subsequently handle those. We've actually just run our 2 largest deuterium-tritium fuel campaigns, which are very high power neutron experiments. So our materials have changed in the last 2 to 4 years, much more than they ever have over the other 40 years of JET lifetime. So it's really important that we've got our modelling sort of quite good for the last 2 years because they have such a huge impact. Tritium is our fuel. It's a gas that gets everywhere. It's a form of hydrogen. It gets soaked into all kinds of things, a bit like water into a sponge, except we soak tritium into metals, we soak it into all manner of materials. They also become inherently radioactive. Tritium retention is really important for not only the safety when we're handling materials, but also we have processes to remove that radioactive gas as part of our waste management process here, and that's really important and unique to fusion. With neutron activation, neutrons sort of fly into materials, nothing like water through a sponge. They just sort of hit it almost like getting a suntan, probably the harshest suntan you've ever seen, and they change the material structure and makeup, and that causes inherent radioactivity in the materials. That is sort of commonplace across the industry. We see it worse here at JET because we've got the deuterium-tritium fuel where it's a lot more high power and high energy. So that's the rough difference. Tritium retention is contamination, activation is actually changing materials at their atomic level.
So we're in the beryllium handling facility at the moment, so we're in BHF3. This is an active area, so we have contamination and radioactive materials within the facility, and we have to process them depending on the job at hand. The sample retrieval material is like a subset of all of the in-vessel materials, so we are proving that the process we want to take to deal with decommissioning of in-vessel materials later on actually works. It's basically pieces of metal and pieces of tiles that were inside the vessel that we have to process, which is size reduction and dismantling. Why is everyone in suits? They're in suits for protecting them against the hazards at hand. So that we've got a beryllium hazard, we've got a tritium hazard with the off-gassing, we've also then got a radiation hazard from the beta gamma that's been emitted from the material. The main aspect of the suits is the beryllium and the tritium hazard. This is the first time this material has come out of a machine in the world that's gone through this process and has been affected in this way. So it's a great research and development opportunity for the future field of fusion. So currently we're in the first phase, which is the pre-detritiation phase, and then we'll go on to the post-detritiation, which approximately is 6 months overall. It's really exciting. I would say that the majority of the people working on this project are from the Waste Innovation Group that's based within TFC, and the whole point of our group is to innovate the future processes of fusion energy and how we deal with waste within the sector.
This is the first material we will have from a deuterium-tritium tokamak to put through detritiation, where it's had significant amounts of tritium through it. So this really does put all of our research and planning for detritiation research into practice. We will get some material to actually check we've done our sums right, check we've done our experiments right, and really demonstrate at full scale. So this is the ultimate test of our detritiation research program. It's incredibly different to other radioactive systems in that we can separate the radioactivity out of our material and hence could significantly reduce any waste that we produce.
Lead QMS and LIPS are techniques that are being developed now for the use in future fusion power plants that will allow us to monitor in real time or near real time the dynamics of accumulation of fuel within the material of the wall. And so the studies of samples that will be removed from JET vessel after the removal campaign will be used in order to support the development of these techniques. This is not a straightforward process. You require quite a complicated procedure and you require quite complicated equipment to do that. And those are the labs that have been doing this in the past for JET components and will be doing it in the future.
The timelines are really fortunate for the UK development of fusion systems. We're decommissioning JET now and we are developing STEP, and the proving of concepts in JET decommissioning is sure to help the development of STEP operations and maintenance. So there is a little bit of pressure just because the timelines are overlapped and because we obviously need to make decisions in the STEP programme that are based on actions in the JDR programme.